Hello students, welcome to the amazing platform of PW English. Today we are on the lecture 2 of electrochemistry, my dear students. Till now we have studied a few important things about electrochemical cells. We have discussed about what exactly is a galvanic cell, what exactly is a electrolytic cell, how do they work, right? We have discussed everything about it. Now since we know what are cells, now let's learn how to represent a particular cell, right? Yes, so today we will be discussing how to represent a cell, and if a cell representation is given, how we can derive that which particular cell it is, right? Yes, so let's start this amazing session, my dear students, with the very high energy. Today we are going to discuss about electrochemical. Okay, no, we've discussed about electrochemical cells. Now we will be discussing about cell notations. Okay, now we'll be discussing about cell notations. What are cell notations? How do we represent these cells and all, right? Yes, so let's start, my dear students. If we talk about a cell, so how you are going to understand it? See, there is a picture and this is of a galvanic cell. Just imagine it is, you have what? Imagine it is a galvanic cell. Okay, so you have zinc sulfate solution here. I told you in galvanic cell you have two different electrodes. This particular metal electrode will be of the same solution which the aqueous solution is, right? Yes, so zinc sulfate solution, so the electrode will be of zinc. I hope it is clear to you. We discussed this in the last class. And if we talk about this particular electrode, we can say that since it is a copper sulfate solution, then the electrode will be of copper metal, right? Yes, till now you don't have any issue. Let me tell you that this is your anode. Okay, it is given here that it is a zinc anode and this is a copper cathode. So now how do you represent a cell? See, you know this particular cell, you know that if this is anode, then IA, we can write the anode reaction here. What does happen on anode? Oxidation or reduction? Ma'am, on anode, it is always and always and always oxidation. So my dear students, here zinc will go into zinc 2 plus aqueous, plus it will lose 2 electrons, because loss of electron is oxidation. So this is the reaction that will take place on the zinc anode. Since this is a cathode, on cathode always and always reduction takes place. And what is reduction? Gain of electrons. So ma'am, copper 2 plus aqueous will gain 2 electrons and reduce into copper solid, right? Yes, so these are the reactions that will be taking place on the two different electrodes. Now the question is how to represent this. Are we going to draw this diagram all the time? No, you only have to represent this cell so that you can deduce all the information just by the representation. So for that, my dear students, there are a few steps. I'll just tell you in the layman language the steps, and then it will be written. You can write those steps also, but for the time being you need to understand this. Okay, how do you represent a cell? The most important thing is, in a representation, my dear students, you put a double line first, and the most important thing is you put a double line. Now what does this double line stand for? This double line actually stands for your salt bridge. Okay, so this is your salt bridge. Always remember that first the double line has to be there. This means that it is a salt bridge. After that, my dear students, to the left, I think this is the left. Yes, I am directionally challenged, I told you. See, to the left, my dear students, of the salt bridge, always and always anode species will come. Whatever the species are present on the anode, those species will be coming to the left of the salt bridge. So I can say that this side will be for anode, and to the right side this will be your cathode. These are the few things which will always be accepted. Okay, you can't change this. You can't write cathode representations here and anode here. No, this is the absolute representation, where this will be your salt bridge, to the left will be anode and to the right will be cathode. Okay, now since you know that on your anode the reaction taking place is zinc goes to zinc 2 plus 2 electrons. This means that you have two species here, zinc solid and zinc 2 plus ions, right? Yes, you have zinc solid and zinc 2 plus ions. So what you are going to do here, my dear students, is that always remember, I am telling you again, always remember, you have to understand it in the same way that when parents and their children go on a walk on a road. If they are going on a walk, what will happen? See, this is the open side which is towards the traffic, and this is the inner side, right? Yes. So parents will always try to keep their child away from the traffic side, and they themselves will walk on the traffic side, right? Yes. Why is this happening? Because ma'am, the parents want to protect their child. Parents want to protect their child. I hope you understand this, because the children get scared fast, right? Yes. The same thing happens here. Your ions are actually your ions are actually small children, and my dear students, the solid state is the parent. Okay, so you know that the ions are little scared, so they cannot be on the outer side, they'll always be in the inner side. Okay, so in the inner side, you'll always first write the ions. Okay. After ions, once you have written all the ionic species, then my dear students, you'll put a line which will represent the phase change. Now I can say that this particular line gives the phase change. Since after that, if in your representation of anode, is there any gas present? If any gas is present, then my dear students, after ion, always your gas will come. Now, since the phase is changing from ionic to gases, that is, ions are in the aqueous state. So from the aqueous state to the gaseous state, phase is changing. So you put a single line. Okay. After that, now you want to write the solid state, right? At the end will come the solid state. Because solid is the parent, he is not scared, right? So always and always ions will come first, then the gases if there are any, and then your solid state. Same goes for the cathodic part. You will have ions first, then you will have gas, and then you will have solid state. Okay? Yes, I hope this is clear to you. Now, my dear students, what I want to tell you is that this is the actual way to represent a cell. Okay. Now, if I have that particular cell which we discussed earlier, this is the cell we have discussed. Now, let's try to write its cell representation. You know that for the cell representation, first and the most important thing is you have to add the salt bridge. Let's add the salt bridge here. After that, towards the left side, we'll write the anode species. So these are the anode species. So we have to write the anode species. First, what will come? Ions. Let's say the concentration of this is given to be 1 molar. Okay. And here also, here concentration is 0.1 molar. Here it is 1 molar. Okay. So now let's write. Now, my dear students, see, towards the left hand side, anode species, and to the anode species, you know that ionic species will come first. So ma'am, zinc 2 plus will come first, and it is in aqueous state. And my dear students, if you see, its concentration is given 1 molar, so you have to write 1 molar concentration too. So you have to write the 1 molar concentration too. After that, see, is there any gas present? No gas is present, then just leave it. Now you need to change the phase, so you'll change the phase, and at the end you'll write the solid state. The solid state is zinc solid, so you'll write zinc solid. This is your anodic representation of the cell. This is the anodic representation of the cell. Now let's move towards the cathodic representation of the cell. You know that in the cathodic representation, the first will be the ion, so Cu2 plus aqueous. And what is the concentration given? 0.1 molar. So you'll write the concentration as 0.1 molar. Then you'll change the phase, and then you'll write the copper solid representation. Copper solid. So this is actually the cell representation. This is how you represent a particular cell. Okay. Now, I hope you've got how you write the cell representation. Okay. Now let's read a little about the rules. Okay. I have told you in the layman language, but if you want to write, you can write it from here. The electrodes are to be placed at the extreme corners. The electrodes are solid, and that is the reason they are always kept at the extreme corners. Next, the LHS, the left hand side, represents your anode, where oxidation takes place. Next is the RHS represents the cathode, where your reduction takes place. The two half cells are usually separated by a salt bridge. That is the double line salt bridge. They are separated by the salt bridge. These are the rules. If you want to write, you can pause the video and write yourself. Okay, I'll just show you whatever we have discussed till now. We've discussed this. Pause the video, write it. Pause the video, write it. And pause the video, write it. Okay. Now let's move forward now, my dear students. I want to tell you something here, that since you had cathode and anode, so the reactions taking place on the cathode and anode individually are called as half cell reactions. This means that if I talk about the reaction taking place only at the anode, I'll say that it is a anodic half cell reaction. If I talk about only the reaction that is taking place at cathode, I'll say that that is the cathodic half cell reactions. In together, they both are known as the complete cell reaction. But when you talk about a particular electrode and its reaction, you say they are half cell reactions. Okay, I hope you're clear with this. Now let's move forward. So now we'll be talking about that how many different types of half cells can be present. How many different types of half cells can be present? Okay, be it anode, be it cathode, different types of half cell reactions can be present. The first is the metal ion half cell. Now, what does metal ion half cell mean? Metal ion half cell means that your electrode is a metal. Your electrode is a metal and aqueous solution of that metal, of the metal. So this is a metal ion half cell. For example, when I talked about the zinc and zinc sulfate solution, when I talked about zinc and zinc sulfate solution, zinc electrode metal and zinc sulfate solution, the same metal ions aqueous solution, right? So that is an example of metal ion half cell. The metallic electrode is immersed in a solution containing its own cations. That is known as the metal ion half cell. If you want to draw it, you draw it, and then I'll give you an example. Okay, I hope you've written it. Now, imagine this is zinc and this is zinc sulfate solution. Okay, so now, my dear students, if this electrode can act as both, it can act as an anode as well as a cathode. Now, imagine if I say it is, let's say this case 1. For case 1, I am saying that it acts as a anode. This particular electrode, metal ion electrode, is behaving as a anode. So if it is acting as an anode, then I can say that for anode, I know oxidation will take place. And if oxidation is taking place, then this means that zinc solid will go into zinc 2 plus aqueous, plus it will gain 2 electrons, right? This is your anodic reaction, oxidation anodic reaction. I hope you're clear with this. You don't have any doubt here. Now, if I ask you that you have to only represent the anodic half cell reaction, you have to only represent the anodic half cell reaction, how are you going to represent it? You can represent it by draw the double line for the salt bridge. I'll say this is a salt bridge, and then, my dear students, to the left of it, all the anode reactions will, all the anode species will come. First, I know that zinc 2 plus ion will come, and then I'll change the phase, and then zinc solid will come. So this is only the anodic half cell representation. So we can say that this is the anodic half cell representation. So this is how you will be representing. This is how you will be representing a half cell reaction. Okay. Now let's talk about the case 2. Now let's talk about the case 2. What if this was your cathode? What if this was your cathode? What will happen now? Let's talk about if it was a cathode. Okay. So ma'am, if you're talking about cathode, then definitely reduction would be taking place. Because on cathode, always and always reduction takes place. What is reduction? Gain of electron is reduction. So this means that this time zinc 2 plus aqueous will gain 2 electrons and it will form zinc 2 zinc solid. This will be the reaction. This is the half cell reaction that will be taking place. Okay. Now you want to give its representation. Then how are you going to give? You will draw a salt bridge. Again, my dear students, a salt bridge, and then you will say that for a cathode, we always write the species to the right of the salt bridge. So this is the salt bridge. To the right of it, first the ions. So zinc 2 plus aqueous, then phase change, then zinc solid. So I can say that this is the cathodic cell representation. So what I want to tell you here by this particular part is that by case 1 and case 2, my dear students, I just want to tell you that a cathode, that a electrode can act both. It can act both as a cathode as a anode. It only depends on how you are using it. It also depends on one more factor which we'll be discussing after the cell representation, which is your EMF of the cell, right? Yes, but we'll talk about it later. But till now you can say that any half cell, any electrode can behave as a cathode as well as a anode. Okay, I hope you're clear with this. If you want to write it, just pause the video, write it, and then we'll move forward. Okay. The other type of half cell is the gas ion half cell. The same cases, it can also act as a cathode as well as an anode. I'll just discuss one and you can write for the other as well. Okay. So since this is a gas ion half cell, what will happen in this particular half cell? Okay. What is this type of electrode? How is this type of electrode? Let's see. You have an aqueous solution and you have a gas. See, my dear students, now you have a H2 gas coming here. You have a H2 gas coming here, or it could be Cl2 gas, any gas. Okay. And you'll have its aqueous solution But the most important thing that you need to understand here is that the electrode will be some inert electrode. The electrode will be some inert electrode. It is a inert electrode. So this time the electrode is not of the metal. The electrode is not of the metal which has the aqueous solution here. No. In the gas ion electrodes, you have a gas, you have its you have its aqueous solution, but the electrode is of some inert electrode. See, you have platinum, you have palladium, you have carbon. These are such inert electrodes which do not react. And since the electrodes are inert, they do not react, then they are good for the purpose, right? Yes. So in the gas ion electrode, you have a gas, you have its aqueous solution, and you have an electrode which is a inert electrode. In this case, you have platinum. Okay. Now, if I talk about this particular electrode and I say that it is acting as a cathode. It is acting as a cathode. So if it is acting as a cathode, can you represent the reaction? Try to do it yourself. I'm not going to write everything for you, give you in a plate, and you will be just like, okay, ma'am, now we can memorize it and go. No, I want you to understand. So try writing the reaction yourself first. Okay. Since it is acting as a cathode, so we can say that if it is a cathode, definitely reduction might be taking place. Because cathode reduction, gain of electron. So this time you have gaining of electron taking place. You know that you have an ion H plus, it is in aqueous state, it will gain an electron and it will give you half H2 gas. It will give you half H2 gas. This is what will happen if your electrode is acting as a cathode. Okay, and if you need to represent it, you can say salt bridge, and then you will have a ion. This is the gaseous state. Just a second. This is the gaseous state, my dear students. You have to write the ion, so you will write the H plus aqueous ion, and then you will change the phase, and then you have, this time you have a gas, so you will have to write the gas here, then H2 gas. But my dear students, at the end, you need to write the solid state. And now you have only your platinum electrode in the solid state. You don't have the metal in the solid state. So this time at the end, you will write platinum solid. At the end, you will write platinum solid. So this is the representation of a cathodic half cell reaction. Okay, I hope you'll write it. Now, can I give you this as a homework, that if it acts as an anode, what will be the reaction and what will be the representation? Let's say this is your homework. This is your homework. So you have to try writing this representation on your own. I hope you will do it. You know this, then you can write this as well. Okay, perfect. I'll just step aside, write this, and then we'll move forward. Okay, I hope you've written it. You've paused the video and written it. Now you have combined the two half cell gas ions. You have gas ion half cells. You have combined the two. Okay, now you have H2 gas here, Cl2 gas here. So both the half cells are gas ion half cells. Okay. Let's say this is your cathode. Let's say this is your cathode. And let's say this is your anode. Let's say this is your cathode and this is your anode. So how are you going to do this particular part? Okay. Whatever we have studied till now, you have to only apply that here. Okay, you can do this. See, you have a node here. So you definitely know that what will happen? Ma'am, oxidation will take place. You know that here oxidation will take place. So let's say here oxidation is taking place. How will oxidation take place? You have Cl2 and you have Cl minus ion. So you can say that, ma'am, Cl minus ion will give you half Cl2 plus electron. Okay, so this is the oxidation that is taking place. Let's come here. This is your cathode. So ma'am, here definitely reduction will be taking place, and for reduction gain of electron will happen. So ma'am, H plus will gain electron and it will give me half H2 gas. So ma'am, this is the representation for the cathode. Okay, this is your cathode, this is your anode. We have written the half cell reactions. You need to write the cell representation. How will you write the cell representation? You just, can I use the red pen now? Let's make the salt bridge first. And then to the left hand side, anodic representation. Anode is that side. So first the ion is Cl minus. So ion is Cl minus aqueous. Then gas, you have Cl2 gas. Then you will write Cl2 gas. If you see, you are given the concentration of Cl minus as 1 molar. So you need to write its concentration as well. Just a second. I'll use this pen for this purpose. Okay. You'll write the cell. Okay, no, this is a little bit. Okay, now you'll write the salt bridge here, and then you'll write the concentration of Cl minus ion, which is 1 molar. Okay, then you'll write the gaseous state of Cl2 gas. Okay, and are you given the pressure? Yes, you're given the pressure 1 atmosphere. So you need to write the pressure conditions as well. Then, my dear students, now ma'am, we've written the ion, we've written the gaseous state. Now you need to write the solid. Which electrode is being used? Platinum. So you'll write platinum solid. This is your anodic representation. Now let's write the cathodic representation. In cathodic representation, you have H plus aqueous. What is the concentration given? See, 0.1 molar. So 0.1 molar. Then H2 gas. What is the pressure given? 1 atmosphere. So 1 atmosphere. And then at the end, you will write the electrode. Electrode is platinum electrode. So platinum solid. So this is how you will be representing a particular cell. This is how you will be representing a particular cell. I hope you're clear with this. I hope you're crystal clear with this part. Perfect, my dear students. If you want to write it, and then we'll move forward. Now, whatever we have studied till now, it is written in the bookish language, so you can just go through it. To represent the gas ion electrode, we must use an inert electrode. For representing a gas ion electrode, you need to represent a electrode such as platinum, palladium, or carbon. Stoichiometric coefficients are never written in the cell representation. I have never written the cell representation. I have never written the stoichiometric coefficient. Just see, here you had half H2, but I haven't written half there. There you had half Cl2. I haven't written half Cl2 there. So the stoichiometric coefficients are never written. Only the ions and the gases are written in the cell representation. Okay, so pause the video, write it. Let's move forward. If the oxidation and the reduced part both are ions, it is called redox half cell. Now, what does this particular line mean? You know what does this mean, but still I'll help you out. Let's say you had zinc that went into zinc 2 plus and 2 electrons. What was this? This was, ma'am, oxidation. Okay. You had the other half cell at cathode where copper 2 plus actually gained 2 electrons and it gave you copper solid. This was reduction. This was reduction. Now, my dear students, actually what happens is when you talk about your net cell reaction, you need to add both of these reactions. Okay. This is taking place on anode and this on cathode. The combination of both will give you a complete cell. And here, my dear students, these two electrons get cancelled and your net cell reaction comes out to be this. What is this? This is your net cell reaction. Okay, so from this, we can say that for a net cell reaction, for a complete cell, you need oxidation as well as you need reduction, right? Yes. So the combination of both, is known as redox. Now, what does redox means? See, this means reduction and this means oxidation. So the combination of oxidation and reduction reactions together is known as redox reactions. Okay, so this is what is given. If the oxidized and reduced part both are ions, it is called a redox half cell. But the one half cell where oxidation is taking place will be a first half of redox half cell. The other will be the other half of the redox half cell. To represent the redox half cell, we need to use the inert electrodes such as platinum, palladium, graphite, etc. I hope this is clear with you. If you want to write it, you can write it and then we'll move forward. Let's move forward. If the physical states are same, the phase bar is replaced by comma. Now, see my dear students, imagine you had a reaction, you had some reaction where Fe3 plus was getting oxidized to Fe2 plus electron. So this is the oxidation taking place, and let me say that this is your anode. Okay, this is the reaction that is taking place on anode. How will you represent this particular half cell on the cell representation? You will say, ma'am, salt bridge. Okay, and to the left will be the anodic representations. Okay, now if you see, you'll say that you have to write the ions first, but you have both ions. You don't have a gas, you don't have a solid, and you have two ions. Till now we were studying only one ion. So if you have two ions, then you need to write Fe2 plus aqueous, and then you'll put a comma, and then you'll write Fe3 plus aqueous, and then you'll write platinum solid. So what I want to say here is that, my dear students, you put a comma as long as the phase is not changing. Since this was aqueous state, this was also aqueous state, the phase is not changing, so you will put a comma. When aqueous to solid, you're changing the phase, then you will put a phase bar. The phase bar will come only when you are changing the phase. Till the phase is not changing, you will put a comma every time. Okay, yes. So this is what it is saying, that if the physical states are same, the phase bar is replaced by the comma. So you put a comma on the place of phase bar. The sequence in the cell notation does not represent the direction of the chemical change. See, my dear students, when we write the cell representation, just say we wrote this cell representation. The direction of the reaction was from H plus to H2. The direction of reaction was from H plus to H2 for the cathode. But my dears, okay, this is saying, go through this. Okay, the direction of the reaction was Cl minus to Cl2, right? But here in the representation, you have Cl2 here and Cl minus here. So what I want to tell you is that the representation does not give you the direction of reaction. The representation only gives you that what all ions and what all gases are present, what all species are present. It doesn't give you the direction of the reaction. Direction of the reaction will be according to anode or cathode, oxidation or reduction. Okay. So now you can read this line. The sequence in the cell notation does not represent the direction of the chemical change. The LHS must involve oxidation and the RHS must involve the reduction. This is the most important thing to understand. Regardless the direction we need to move. Regardless the direction we need to. It is clear with you? I hope it's crystal clear with you. Perfect, my dear students. Very good. Now let's move forward. Pause the video, write it, and then we'll solve few questions. Let's solve a few questions. I hope the question is visible to you. If the question is not visible, I'll just dictate the question. Question says that represent the cell from the following cell notation. The cell notation is given and you have to represent the cell. What is the cell? You have H2 gas, you have Cl2 gas, and it is giving you 2H plus plus 2Cl minus. So this is the reaction, and now you have to find that how you will give the cell representation. Okay, I told you in the net cell reaction you don't have oxidation or reduction, you have the complete combination of the both. So now, my dear students, what we will do is we will separate the reactions. You will have H2 to you will have H plus, and then you will have Cl2 to Cl minus. Okay, now let's see what is happening. Okay, since here is H2 and here is electron, so I have to add a electron here in order to balance the charges, and here half will come. This is how you balance, right? Yes. So can I say that here loss of electron is taking place, loss of electrons. So what is this? This is anode. Why? Because oxidation is taking place. Now try to balance that yourself. Since there is a negative sign, so you can add an electron to this side. So you'll add an electron this side, and you'll also have to, just a second, huh? You'll have to add half here, and then you'll have to add an electron here. This is how your reaction will be balanced. Now if you see here, you can say that gain of electron. This means that reduction, and if it is a reduction, then it is a cathode. If it is a reduction, it is a cathode. Now you have to represent the cell. You have cathode, you have anode. What is the big deal? You'll write a salt bridge. To the left hand side, anode species. This is your anode. First you will write H plus aqueous. Then you will write H2 gas. Now, my dear students, you're not given about anything about the electrode. Write any electrode you want. Let us say platinum solid, inert electrode. Okay. Now let's talk to the cathodic side. Cathodic side, you have the ion Cl minus aqueous. You have the gas Cl2 gas, and then platinum solid. So this is how you represent a particular cell if you're given in a question. I hope it is clear to you. Can I have some water? I'll have some water. Try to do the next question. Okay. Pause the video, do this, and then try to do the next question. Next question. The question is, I'll write the reaction. Zinc solid plus 2H plus aqueous is giving you zinc 2 plus aqueous plus H2 gas. Okay. So this is here on your screens. Try to do this question. Okay. I hope you've paused the video and tried this question yourself. Now I'll try. See, now I'm going to show you how you can do these questions a little faster. You know that you have to compare these two, and you know that you have to compare these two. See, zinc is going to zinc 2 plus. If here the oxidation state of zinc is 0 and here it is plus 2, this means that zinc has lost 2 electrons. So can I say that this is loss of electron? And if it is loss of electron, can I say this is oxidation? See, H plus is going to, here the oxidation state is plus 1 and here the oxidation state is 0. So you're going from plus 1 to 0. This means that gain of electron. And if it is gain of electron, can I say it is reduction? Can I say it is reduction? Yes, you can say it is reduction. Okay, so now we can write anode and cathode reactions. You will have anode here, oxidation, and the reaction will be zinc goes to zinc 2 plus 2 electrons. If you talk about cathode, then reduction is taking place. What is happening? H2, you have 2, so 2H plus 2 electrons is giving you H2, right? Yes. So now you need to represent the cell. So you will add a salt bridge, and to the left hand side you will write the anodic reactions. Your anodic reaction is this zinc 2 plus aqueous. Then you have zinc solid. So this time you have zinc solid, so you need not write platinum electrode. Let's talk about cathode side. You have the ion H plus aqueous. Then H2 gas. So I'll write H2 gas, but now ma'am, still now we haven't seen the solid state. So we'll write the electrode, any inert electrode, let's say platinum solid. So this will be the representation of the cell. This will be the representation of the cell. This is how you have to solve these questions. Easy. I know it is easy, my dear students. You just need to apply a little of the concept. Let's move forward to the next question. Pause the video, write it, and then we'll move forward. You have a question here. You have a question here. It says that copper solid plus Cl2 gas goes to copper aqueous plus copper 2 plus aqueous and 2Cl minus aqueous. Okay, you have to represent the cell. You only have to represent the cell. Okay, so let's try this question. Copper solid plus Cl2 gas gives you Cu2 plus aqueous plus 2Cl minus 2Cl minus. Now let's try to do this question ourselves. Okay, see, copper to copper 2 plus Cl2 to Cl minus. See, copper oxidation state 0 plus 2 state means this is loss of electron. So this is oxidation. Cl2 0 oxidation state to -1. This means that it might have gained an electron. So gain of electron. So gain of electron. This is reduction. This is reduction. Okay, perfect. Now I know oxidation and reduction, so I can say anode oxidation. So copper goes to copper 2 plus 2 electrons. Cathode reduction. So for reduction, Cl2 goes to Cl minus 2 plus 2 electrons. This is my anode and cathodic reactions. I have to represent this. Let's represent it, my dear students. I'll add a salt bridge here. Anodic reaction, copper 2 plus aqueous. Then I have copper solid. So here copper solid. See, on the cathode, ion is Cl minus aqueous. Then you have Cl2 gas. But now you need to write a electrode. Now, my dear students, you could have written platinum solid. That would have been correct. But since you see the options, you have only carbon solid as inert electrode. So this time you will have to write here carbon solid. If the options were not given, you could have written platinum. That would have also been correct. So now let's see which representation is correct. Copper solid, then copper 2 plus, then Cl minus, then Cl2 gas and carbon solid. So option A will be your correct answer. Option A will be your correct answer. So this is how you are going to solve these types of questions, right? Yes, perfect. If you want to pause and write, pause the video, write it, and then we'll move forward. Next, you have another question, a very important question. The question says that you are given the cell representation. You are given the cell representation and you have to give the cell reaction. You have to give the correct cell reaction. So first, I have been given the cell representation. Let me find the net cell reaction. Okay, see, I know that this is salt bridge, and then I know that this is anodic part, and then this is cathodic part, right? Yes. On anode, what happens? Oxidation. So I'll write anode oxidation. And since oxidation is taking place, I have two ions. Then Fe3 plus might have, sorry, Fe2 plus aqueous might have lost one electron and given you Fe3 plus aqueous. This is what is the oxidation reaction, right? Let's talk about, sorry. Let's talk about cathode. Cathode is reduction. At cathode, reduction takes place. I have this species here. So definitely Fe2 plus might have gained 2 electrons and given me Fe solid. So this is how the reduction reaction takes place. Now, what important thing you need to understand here is, my dear students, that this is your first reaction, this is your second reaction, and you need to add the reactions and give me the final reaction. Okay, so the reactions are Fe2 plus gives me Fe3 plus plus electron, and here the reaction is Fe2 plus plus 2 electrons, and they are giving me Fe solid. So now, what most important thing you need to understand is, my dear students, whenever you add two cell reactions, cathode and anode, always remember the exchange of electrons should be equal. There should be no electron present in your net cell reaction. So if I see here, electrons cannot be cancelled out because here are 2 electrons, here are 1 electron. So what you need to do is you need to multiply this particular reaction by 2. So that you will have two electrons each and they'll get cancelled out. If I multiply this whole reaction by 2, then here 2 will come, here also 2 and here also 2. Then this will be cancelled and my net cell reaction will come out to be 2 Fe2 plus 2 Fe2 plus, what have I done? Just a second. Huh? Yeah, 2 electrons get cancelled. Right now net cell reaction, you have, these are 2 Fe2 plus and this plus 1, 3 Fe2 plus gives me 2 Fe3 plus Fe, right? So this will be your net cell reaction. This will be your net cell reaction. So you just need to understand that in net cell reaction, there should be no electrons present. If there are, then you need to multiply the half cell reactions and cancel the total number of electrons. Okay, yes. So let's see which option is correct. 3 Fe2 plus gives Fe plus 2 Fe3 plus. Option B will be your correct answer. Option B will be your correct answer, right? Yes. So if you want to write it, please write it and then we'll move forward. Okay, let's start. Now, my dear students, we'll be discussing a very important topic. Again, see, what is this? This is the place where we use electrochemistry concepts a lot. So I just brought this picture. Okay, what important thing we are going to study is this EMF. I told you about the cell's EMF. See, my dear students, every cell, every whole combined cell has its EMF. Okay, whole cell has its EMF. Also the half cells also have their EMF values. Okay, these EMF values actually tell us whether a reaction will be spontaneous or non-spontaneous. Okay, so now we need to understand a little bit about this EMF. Okay, so let's start this topic. We'll start today, but we'll have to continue it to the next session as well. Okay, so now the first question that arises, and it is very important question because this is generally asked in your competitive exams, that what are the factors on which your EMF depends? What are the factors on which the EMF of a cell depends? So the EMF of the cell actually depends on the nature of the chemical reaction. Every reaction has its individual EMF value, right? Yes. Similarly, it also depends on the concentration of the reactants and products. In a particular reaction, you have different concentrations of different reactants and products. Your EMF value will change. So it depends on the nature of the reaction. It depends on the concentration of the reactants and products. It depends on the pressure of the gases. If you have any gas in your reactant or product, it will depend on the pressure of that gas as well. So this means that it depends on the reactants and products concentration or their pressures if they are gases. And also it depends on the temperature at which you are performing that particular reaction. So there are the four major factors in nature. Then it depends on the concentration of the reactants and products. If you have gases, then it depends on the pressures of that gases and the temperature. This is the most important thing. See, since there are so many factors, so we can't study it on all the temperatures and pressures, right? Yes, we have to find some solution to it. So scientists tried to calculate a standard EMF of each cell. So they tried to calculate a standard EMF of each cell. Then if we'll change the concentrations, definitely the values will change. But let's calculate on a particular temperature and concentration and pressure values, what different reactions have their EMF values. Okay, so what did they do? They created a SATP condition. What is SATP condition, my dear students? Scientists tried that let's fix the concentration. Let's fix the concentration to 1 molar. Be it a reactant, be it a product, if it is an ion, it will have a concentration of 1 molar. Let's fix the temperature to 298 Kelvin. Let's fix the temperature to 298 Kelvin. Let's take the EMF of all the reactions at 298 Kelvin. and then they fixed the pressures of the gases at 1 atmosphere, which is nearly equal to 1 bar. Okay, so what they do, they took the pressure conditions to also to be fixed. So except the nature, they have fixed all the three parts. Okay, yes, because with nature obviously EMF will change. If we'll fix the nature also, then only one value will come, right? Yes, so we fixed the three parameters and tried to calculate these EMF values of all the reactions. And my dear students, the EMF calculated, the EMF calculated at this SATP conditions is known as standard EMF, is known as the standard EMF of cell. So for every cell, they will have a definite standard EMF. Okay, so this is what is known by the SATP conditions. SATP actually stands for standard ambient temperature and pressure. Standard ambient temperature and pressure. Just you need to know that at a fixed temperature pressure conditions, they calculated the standard EMF of all the cells. On the basis of that, they just characterized all the cells. Okay, yes. If you want to write it, you can write it, and then we'll move forward. Let's move forward, my dear students. If you want to write this, you can write this as SATP conditions. What do SATP condition stands for? SATP condition stands for if all the reactants and products are present in their respective standard state. Standard state means temperature and pressure conditions and concentration. The EMF calculated will be known as a standard EMF. Standard EMF has a constant value for a given reaction. Obviously, you have fixed the three conditions, then the value will be constant for every reaction. Okay, perfect. Let's try to calculate the cell EMF. How are we going to calculate the cell EMF? How will we calculate? See, you have a instrument where you put a cell and you get the standard EMF of that cell. Okay, but you have to know mathematically how that EMF can be calculated or how you're going to use that EMF. Okay, so now my dear students, you have a cell present here. Can you see the cell? Just a second. So can you see the cell? Yes, you can see the cell. And this is a galvanic cell. This is the actual galvanic cell. Okay, you have your zinc sulfate solution here, you have zinc electrode, you have a copper sulfate solution here, you have a copper electrode here, you have a salt bridge, you have aqueous solutions there, right? Current is flowing, that is the reason the bulb has blown, right? Yeah. So what I want to tell you here is that, my dear students, just see, just have a look here. I can say that for this cell at anode, oxidation was taking place. Right? Yes. And I can say that at cathode, reduction was taking place. Yes, ma'am, you can say that. Okay. Now, what I want to make you understand is, my dear students, now for this particular cell, you have a EMF of a cell. We'll say that here E0 will be the standard EMF of cell, which will be calculated, which will be given to you by the instrument. Okay, so what is the role of anode and cathode here? The major role of anode and cathode is that, my dear students, you know, you are given E0 values. How you are given E0 values? I'm just going to tell you that. Imagine you are given the EMF value, E0 value as zinc 2 plus, or it is given like this, zinc 2 plus. This is, let's say, 0.76. Okay, yeah. So now what you can understand from this is, let's just leave it here and I'll make you understand this part. What you can understand, if you are given in a question something like this, so this means that this particular, my dear students, this particular part gives you the direction of your reaction. In the representation of E0 values, you are actually given the direction of reaction. Okay, so this E0 value is for zinc 2 plus 2 electrons, and this E0 value is 0.76. So my dear students, I can see oxidation is taking place. So this is the oxidation potential. This is the oxidation potential. This is the standard. This is the standard oxidation potential. So the E naught values actually give you that how to, what extent that reaction can oxidize or reduce. Here the extent that it can oxidize is 0.76 volts. Okay. Similarly, if you were given, let's say you are given E naught value for copper to copper 2 plus equal to minus 0.34 volt. Okay, I don't remember the exact value, but I think this is the value. So the E naught value for copper to copper 2 plus is given to be minus 0.34 volt. So now from this, what you can understand is that, ma'am, this will give me the direction of the reaction. So this means that copper to copper 2 plus 2 electrons, here E naught value is minus 0.34 volt. Okay. So now what I want to say you is that you can see the E naught value and you can understand that since it is a positive value, so it is spontaneous. If your E naught value is positive, that means it is spontaneous. Zinc wants to get converted into zinc 2 plus, and that too with 0.76 volt. But if you talk about copper to copper 2 plus ion, my dear students, this is a negative value of 0.34. Since it is negative, this means that copper don't want to get converted into copper 2 plus. It doesn't want to get oxidized. It doesn't want to get oxidized. And this is what I told you in the starting phase. I told you in the last class, I told you that you have to accept what I'm saying, that zinc wants to get converted into zinc 2 plus. That is, it wants to get oxidized. But copper doesn't want to get oxidized. Okay. Now, this is actually, my dear students, the oxidation, standard oxidation potential of copper, right? Yes. So this is the oxidation potential. But ma'am, how is the reduction potential given then? Let's see that now. If you talk about the reduction potentials, then my dear students, this will be given as E naught, zinc 2 plus to zinc, and this value will be minus 0.76 volt. And here E naught, copper 2 plus to copper, and this value is 0.34 volt. Now again you will say that this is giving me the direction. So zinc 2 plus will gain 2 electrons and it will give zinc, and the E naught value is minus 0.76 volt. If I talk about this, then copper 2 plus will gain 2 electrons and it will get converted into copper, and the E naught value is 0.3. So if you see here, my dear students, this is giving you the standard reduction potential, because the direction gives me the potential, right? Yes. Same way, this also gives you the reduction potential. Now just see. Here, this value is negative. This means that zinc doesn't want to get reduced. It doesn't want to gain electron. But copper 2 plus reduction potential is positive. This means that copper wants to get converted into copper, and it wants to gain 2 electrons. It wants to get reduced. If you see, very important thing, that my dear students, this is the oxidation potential of zinc and this is the reduction potential. And we see that if one element wants to get oxidized, if its oxidation potential is more, then definitely its reduction potential will be the opposite sign of that. From here, you have deduced a very important thing, that standard oxidation potential is always equal to the negative of a reduction potential. So if you know any species oxidation potential, you can find its reduction potential. If one of them wants to get oxidized, then it will not want to get reduced, right? Yes, this is the most important thing that we needed to find out. Okay, just see, if oxidation potential was 0.76, then reduction potential is minus 0.76. Here oxidation potential was minus 0.34. It doesn't want to get oxidized, but it wants to get reduced. It is plus 0.34 volts. This is how oxidation and reduction potentials are studied. Okay. And my dear students, with this you know that E naught of cell is the standard, it is the standard EMF of cell. And this standard EMF of cell has a formula. This standard EMF of cell has a formula, and this is equal to E naught reduction potential of anode minus E naught reduction potential of cathode. I'll write it here as well. This is the formula of calculating E naught of cell, okay, where E naught Rp of anode means that standard reduction potential of anode, and E naught Rp of cathode is the standard reduction potential E naught reduction potential of E naught of cell is equal to E naught reduction potential of cathode minus anode. Reduction potential of cathode. Okay. Okay. I hope this is clear with you. I hope this is clear with you. This here, my dear students, you just need to change it. I'm sorry. It will be E naught reduction potential of cathode minus E naught reduction potential of anode. Okay. This is the E naught formula which you need to use again and again for calculating the standard EMF of cell. Sometimes you will be given two things out of these, and third you have to calculate. This is how you calculate. Okay. I hope you're clear with this. I hope you're clear with this. Perfect. Now let's move forward. Now, my dear students, here we have studied that whenever Gibbs free energy is negative, reaction is spontaneous. Gibbs free energy is positive, reaction is spontaneous. Sorry, non-spontaneous. But what if you're not given delta G and you are given EMF of cell and you have to find that whether it is spontaneous or not? Then you have to calculate using this. Okay. If you are, my dear students, calculating with the EMF of the cell, then if you have a positive EMF of the cell, then the reaction will be spontaneous. A reaction with the positive EMF of the cell will be spontaneous. That is, E naught of cell should be positive. Okay. And for non-spontaneous, E naught of cell should be negative. So you can calculate by Gibbs free energy, and if you're not given Gibbs free energy, you can also find out by finding the value for EMF of the cell, right? Yes, I hope you're clear with this. If you want to write it, and then we'll move forward. Oh, you've not written this as well. You can write this also. You can write this, and you can write this. Okay. Let's try to solve a few questions and then we'll move forward. See, now you have a question. What does the question say? Question says that you are given a cell representation. Write the cell reaction and find the E naught of cell. You have to calculate the E naught of cell and you are given some E naught values here. Okay. Let me try this question. Next question will be a homework. Okay. So now I know that this is my salt bridge. This is anode and this is cathode. So here oxidation will be taking place. So my anode reaction will be zinc goes to zinc 2 plus 2 electrons. And if I talk about cathode, then reduction takes place. That is my cathode. So copper 2 plus will be gaining 2 electrons and it will give me copper solid. My dear students, for combining for the net cell reaction, you need to combine both the half cells and you need to see whether the electrons are equal. Yes, the electrons are equal. They'll get cancelled out. The net cell reaction will be zinc plus copper 2 plus will give you zinc 2 plus copper solid. So this is your net cell reaction. So now what you need to find out is, you need to find out the E naught of cell. For calculating E naught of cell, I know that it is equal to E naught reduction potential of cathode minus E naught reduction potential of anode, right? Yes. So you need reduction potentials of cathode as well as anode. If I see here, my cathode is copper. So is this the reduction potential given? See, copper 2 plus 2 copper. Yes, ma'am, this is the reduction potential. So this is 0.34 minus. You need the reduction potential of anode. But can you see that this is not the reduction potential? This is the oxidation potential. So you need reduction potential. So reduction potential will be E naught of reduction potential will be equal to minus of E naught of oxidation potential. So can I say that E naught of zinc 2 plus to zinc will be equal to minus 0.76 volt? We can say this. Yes. So you'll write minus 0.76. This will be 0.34 plus 0.76. Right? You'll add this and you'll get your, E naught of cell. It will be a positive value. So the reaction is spontaneous. Such a easy question. Right? Perfect. Yes. Let's move forward to the next question. If you want to write it, and then we'll move forward. Next question. Here is the question. Try to do this question yourself. This will be a homework question because we have done these types of questions now. You need to calculate the E naught of cell. I hope you will all calculate it. Very good, my dear students. Let's move forward. The next question is that you are given two reactions and you are given E naught values of both. You have to tell which reaction is feasible at cathode. You have to tell which of the following reaction will take place at cathode. More feasible to cathode. Okay. So for this, I know that on cathode, always what happens? Reduction takes place. So if a reaction has more reduction potential, it will be more feasible. So you just need to see that which of the following has a greater reduction potential. Okay. If you see the reaction, is this reaction reduction? Yes, ma'am, it is gaining electron. It is a reduction reaction. It is also gaining electron. It is also a reduction reaction. So these both E naught values are, this is also a reduction potential and this is also reduction potential. Just see which of the following has a greater reduction potential value. So which has a greater reduction potential value? 0.80 volt, because that is of plus, right? So we can say that Ag plus electron to Ag solid is more feasible at cathode. And if we had asked which of the following is more feasible at anode, then what you had to do? You just had to see that which of the following had the lesser reduction potential. Which will have a lesser reduction potential? Obviously, it will have a more oxidation potential. So lesser reduction potential was this. So this would have more oxidation potential. So this would have been a better choice for the anodic reactions, right? Yes, perfect. This is how you solve these questions. So easy question. You just need to understand the concept, right? Yes. You can write this and then we'll move forward. Okay. So now, my dear students, again, this will be your homework question. You have to do this question on your own. Exactly like how we discussed the last question. You have to solve this question on your own. So you can pause the video, try the question and let me know in the comment section. Okay. So with this, my dear students, we come to our end of the session. So I hope you enjoyed today's session. You studied something new. You explored the beauty of chemistry, actually, because it is the most beautiful part. It is such an easy subject. I don't know why people think that chemistry is not easy. It is such a beautiful subject, right? I hope you agree with me, because I am trying to make you fall in love with chemistry, because chemistry is the best part. It is so easy. You only need to understand the concept and then the questions will be like this. I can do every question, right? Yes. So my dear students, try to enjoy this subject, and the subject will also definitely will give you back. It will give you a lot of marks and you will be happy, right? Yes, I'll be happy. So keep enjoying, keep studying. We'll meet in the next session. Thank you so much. All the very best.